maintainer in the hypervisor. So today I'm going to be talking about migration v2. So this is something that's been brewing for a while, and the first question really is why migration v2? So this started around about 18 months ago. So around January last year, we just released XenServer 6.2 with a 64-bit Xen. Xen has always been 64-bit in XenServer, but even in XenServer 6.2, we still had a 32-bit DOM0 because partly because of inertia. It had been 32-bit for a very long time. There were some issues in upgrading some of the packages, but also there are a number of things that are still present in 32-bit architecture that makes it more efficient to virtualize. So unless you need stupidly large quantities of RAM, you can still easily get away with a 32-bit DOM0 today. The real thing that we hit was Ivy Bridge servers that had the high MMIO hole above 2 to the 44 bits in physical address space, and that's a limit of 32-bit PV guests. So we needed to switch to a 64-bit DOM0 to support Ivy Bridge servers that were becoming available whilst we were developing. So for XenServer 6.5, we switched DOM0 to 64-bit. Now we then went and did some tests because we're nice like that. One of the tests we've got is the rolling pool upgrade test. So this is all automated in our automated framework. And it generates a pool of Xen servers, starts off at XenServer 6.2, installs some virtual machines into them, then starts upgrading them each in turn to XenServer 6.5, migrating the VMs as they go. We got a bit of a curious error that looked a little bit like this. Now, the middle line there, the P2M size, is the size of the virtual machine. You'll notice that's a little bit big. So we had to investigate. Quick show of hands, who here can write C? That's a lot of you. C in a Unix environment, I'm guessing fairly similar. Right. Those of you who don't know the answer to this already, can anyone spot the bug in this bit of code? The bottom line here is the curious print message from before. Anyone? Size of unsigned long is 32 bits in 32-bit and 64 bits in 64-bit. We were a little bit of a shock to discover this in a bit of code that had basically been working for a long time. It's one of these areas. If it hasn't changed in a very long time and it sort of kept on working, it must have been fine, right? Not so. We actually, at this point, we sat down, had a look at what was actually there. There's absolutely nothing written down. Well, there is. It was reverse engineered from the code about 7 years later. There is literally no header information at all. The first item of information in the migration stream was that P2M size, which is the size of the virtual machine. It was a little bit tricky to edit. I think more bug fixes to it had to have a further bug fix on top of them than the first way around. It was two huge functions with a mess of goto statements in it. That's definitely goto abuse. And during this time, we gained some more hypervisor support for debug registers in AMD systems, and attempting to extend the support to include that was sufficiently complicated that we gave up. So that's all fixed in V2. It's fine and working, but it was literally too complicated to do a backwards and forwards compatible method in legacy migration. The other thing that happened is the asymmetric handling of the QEMU record. I think this is a side effect of when Remus got added, where there were multiple QEMU records in the image. So what happened was the save side had the caller, so ZenD or LiveXL, put the QEMU record in, whereas the restore side had the low-level code pulling it out, saving it in a magic file. But the biggest problem was the fact that the stream was not equivalent between a 32 and a 64-bit compilation. So we decided to do a bit of work. As a slight tangent, this is what is needed for live migration. It's actually a very simple algorithm. The information needed looks a little bit like this. There's lots of page data because VMs tend to have some RAM. At the moment, all migration is specific to x86, but that has been abstracted out. The TSC information here is common to x86 guests. It will not be present in ARM guests if and when that happens. HVM guests have the set of params that goes with them, and it's got a Xen blob. The Xen blob has a load of architectural state and the various devices that Xen emulates, so the virtual local APIC, virtual IO APIC, virtual HPET, and stuff like that. That's essentially a blob of data you hand back to Xen, and Xen deals with it. PV guests are a little bit more complicated. They've got far more bits exposed. So there's the width, which is 32 or 64-bit, levels, which is the number of levels of page tables, so 3 or 4 at the moment. There used to be support for 2, but that disappeared when we got rid of the 32-bit hypervisor. There's various information about the P2M. So this is the pseudo-phys to machine mapping table that lives inside PV guest, and normally it's private to the PV guest until you migrate it, at which point the tool stack needs to go and have a peek at it to get everything in order. There's various assorted bits of vCPU state and the shared info page that moves across. Now, we use the same algorithm for both live migrate and suspend to disk. Essentially, you're either piping it into a file or piping it across the network and undoing it on the far side. It's the same algorithm. So suspend is very easy. You just pause the VM, have some of the head metadata at the start, put all the memory in, tail metadata on the end, and it's all fine. Live migrate's a little bit more complicated, but again, still fairly simple. So the hypervisor provides logdirty support, which tracks writes to the pages of the guest. You turn on logdirty to start with, copy all of the memory once, and then just loop a few times, asking the hypervisor for the dirty pages. And the idea is that over time you get down to a small set of pages, you pause the VM, and you copy the remaining bit of memory. And the key point here is to have the VM paused for the least amount of time going, because that's time when your VM is not responding. And the whole point of a live migrate is to attempt to keep it live whilst it's moving. I'll get back to a couple of bits of that later. What we had to do for xenserver was a little bit radical. We decided that what was currently there was sufficiently broken that it couldn't be fixed, so we applied some engineering to the problem. And we designed Migration V2 completely from scratch. Started by writing it down. In fact, that document was written before any code was written. It has some headers in it, which we'll look at later. It has an exact binary layout, and it was specifically designed to be extensible going forwards. The specification also includes how you can improve, how you can make improvements going forwards. Then we re-implemented everything completely from scratch because none of the code was salvageable. There were a few bits and pieces in there that had been bugs from 2002 that had been committed in, reverted 3 hours later, but not quite fully reverted. And then there was a particularly curious macro that's been around for the past 12 years, doing something specifically unrelated to what it claimed in its name. So there was a huge amount of code archaeology involved. But what we have now in the V2 implementation is a completely generic save and restore algorithm that has no architecture-specific knowledge whatsoever. So this is the loop over memory and various bits and pieces. The architectures are pulled in by some specific stubs. So at the moment we have the x86 PV stubs and the x86 HVM stubs. ARM support will be very easy. Copy the HVM stubs, run some sed over it, and that will probably work. So we've got a split now between the live migration algorithm and the implementation for different guest types. That was previously missing. Previously, everything was completely x86 specific, and there was one previous attempt to do ARM that essentially rewrote it from scratch but copied the old way. So this leaves us in a bit of a problem. We've got ourselves a brand new, shiny Migration v2 and a load of customers still using the old system. So we wrote a bit of Python. Well, I wrote a bit of Python. It's called this. It's committed into the tree, and it is specifically designed to pipe a legacy stream to a v2 stream. Part of the design we did was to make this conversion easy. So there were a couple of things where we followed the old way, where ideally we'd have done it differently, but it made it far easier to convert. This conversion stream needs two extra pieces of information. It needs to know whether the guest in the stream is HVM or PV, and it needs to know the width of the tool stack that saved the image. It turns out that it is there's insufficient information in the head of the stream to automatically work this out, particularly if you need compatibility before Zen 4.3, which we, Zen 3.4, which we still have in xenserver. So we decided to go to unanimously requiring the tool stack to provide those two bits of information, and then various assumptions are checked throughout the stream. So if you get it wrong, it'll tend to tell you, but it will not make a guess and risk getting the guess wrong to start with. So this actually was all we needed for xenserver. So about a year ago, we were complete, tested, it all worked fine. I think there was only one bug raised against it, which was quite nice. So this is an example of what it looks like. There are two headers in the stream. There's the image header that describes the stream itself, and the domain header that describes the virtual machine. And then we've got a number of records on the end. The image header has a marker of 64 bits worth of ones. That is the only thing that you can unanimously distinguish a legacy stream from a v2 stream. There is no valid legacy stream that has all bits set in the first 8 words, which is nice. That is literally there just to prevent things going wrong. It'll blow up quite spectacularly if you get that the wrong way around. So it's just there to be absolutely certain you don't mix the streams up. Then there's an ID that happens to be Zen F in ASCII because we were lazy like that. Actually the version was version 1 until we realized we were calling it Migration v2. We might as well make the version the same as what we were naming it. Options has the endianness. So another thing we decided to do was actually follow network order, certainly for the start of it, before you can say this is a little endian system. We're not aware of any big endian systems out there, but there's one bit in the options that covers all of that. The domain header describes the domain, so there's a domain type field where we've got PV, HVM. I think we also specified PVH and ARM in there as well. Because we felt it was worthwhile to do. Page shift is usually 12 to indicate 4K pages, and there's a hint at the version of Zen that this was saved on. So we hope never for that information to be useful. Oh, right, okay, I've got to keep on moving the mouse. Sorry about that. We hope that information is never used, but it does provide a hint in the case that we need to in the future. And also, it's useful for the logs to see whether this was an import from an older version of Xen or a migrate on the same version of Xen. It's useful for debugging if something's gone wrong. Then we have a load of records. Now, every single record in this has a type and a length, which makes it a properly tagged stream, and everything's rounded up to 8 octets in the end, because that makes life simple if you're the kernel shifting data around. Certainly makes it efficient. And there are a number of records. These are all written down in the stream specification, as well as a standard a suggested order of records. Now, that was all we needed to do for xenserver. By this point, we had xenserver working perfectly well. If you were doing an upgrade from an older version of xenserver, you knew it was 32-bit, and this was working fine. But there's a little bit of a problem here. We didn't want to be maintaining our own fork of live migration, so we had to go and upstream it. Then we started looking at LiveXL, because in the intermediate time, Xendi had gone and died a violent death, and LiveXL was around. So up until this point, LiveXL had absolutely no participation in the stream. It literally handed the file descriptor all the way down to the bottom layer. And then there was this tool stack data thing that was put in later. Turns out there were several bugs in the LibXL side of that. There was a structure that had an extra 4 bytes on the end of it in 64-bit because of standard alignment, and there was some particularly dodgy pointer arithmetic, which leaked a bit of heap into the stream, but we'll wander over those. I would say we redesigned it from scratch, but there was nothing there to start with, so we just designed it from scratch, and we went and wrote it down. Curiously, it looks rather similar to the libxc format. It's got slightly different header layout because it needs it, but it's a standard type length chunks. It's extensible. It does not depend on the compilation ABI. And I would say we also rewrote it from scratch, but we just wrote it from scratch. The other thing that happened was we extended the conversion script. So the conversion script can now convert legacy libxc to new libxc, or legacy libxc to new libxl. It specifically relayers the QEMU and toolstack records that have logically moved up a layer in the format. So here's an example of what it looks like. This is looking at the framing of the stream. So legacy migration had, assuming libxl toolstack here, XL can be logically replaced with libvirt or zappy or whatever else. In the XL case, there's the header, and then there's the optional data that's a little less optional than its name implies. That's the domain configuration file. And then immediately after that, there's the libxc bits and pieces. The dots I abbreviated hundreds of thousands of page data records for brevity here. That's the bits that are basically going to stay the same across all of them. You also had the toolstack blob in there and the QEMU blob that we dealt with. So in Migration v2, it looks a little bit like this. We've now introduced some libxl.
Earlier you mentioned that part of migration is a looping around.
Yes.
Was the header optional data and so forth redone every time, or was there?
No, so the loop over memory is all in libxc, so the yellow bit. And that's abbreviated by a whole lot of dots. Actually, before they're the dots before the toolstack record. That's where the vast majority of the data actually resides.
And then the migration, you got dots, okay?
Yes. So The entire point of doing Migration v2 was to have a functional equivalent that worked, basically. We were specifically not adding in new features for the sake of new features. So in Migration v2, we've now introduced some LibXL bits. So there's the LibXL header, and one of the LibXL records is a record saying, hand me to libxc, and libxc knows how to deal with the rest of it. So you go the XL header, the optional data, the libxl header, libxc content, and now you're back in essentially the same position as we were before, except it's now using the v2 stream. You wander all the way, and there's actually an end record. Previously, there was absolutely no end record in the stream, which was another interesting point of actually working out when you'd completed it or not. Now there's an explicit end record where libxc signals that it's complete. It hands back up, and we've now got the emulator xenstore record, which is the logical successor to what was previously called the toolstack record. And the emulator context that was previously called the QEMU record. So one thing we did do when specifying this is add in logical support for multiple emulators. At the moment, Upstream only has support for one emulator, but in xenserver we've already got 2 emulators in certain cases, and this is something we are going to be working on upstreaming soon anyway. So we decided just to put in support for that straight away now rather than fixing it later. It was very easy. You've just got an extra index in the record. So here's an example of what it looks like with Remus. Remus is slightly different. Remus starts up and then keeps on sending data until the sending side dies. So we extended the base migration slightly. libxc gained the checkpoint record, and libxl gained the checkpoint end record. And they basically used just to switch ownership of the stream between the 2 pieces. So the libxc checkpoint in yellow there indicates that there is a consistent view of memory and vCPU state. Then you hand back up to libxl that for a PV guest, there's only the checkpoint end, there's no extra information. For an HVM guest, you've got an emulator context and an emulator xenstore record, so a couple of K of data. And then a checkpoint end that signifies that libxl thinks that there's a consistent state. Then you resynchronize forwards and then loop until the sending side dies. So that's pretty much it. There are a couple of things of note that I bring up here. Whilst doing this, we found many bugs. There were some hypervisor side ones, some generic libxengest bugs. We fixed all of those as we were going along. I think there are something like 27 individual bugs in total that we got. One in particular was the way in which vCPU state was got for PV guests. There were a number of situations where you could get truncated state on the receiving side, and there were certain situations where if you interleaved a migrate with a specific vCPU action, you could get corruption going on there as well. So that's all completely fixed now. PV guests and super pages. This came as a little bit of a surprise. There is support for PV guests and super pages, but no one ever put 2 and 2 together when migrating them. It is impossible to migrate a PV guest with super pages. You can save a super page fairly easily, but you cannot guarantee to restore a super page on the far side. And as PV guests have their page tables rewritten by the migration stream, you need to put a super page back in the same position, and there is absolutely no ability to fragment the super page if the receiving side does not have enough free memory available. And there is literally nothing you can do in that scenario. what used to happen was that your PV guest would resume and it would suddenly be missing 2 meg of data, and then your kernel would probably hit a page fault shortly afterwards and get a little bit unhappy. Whilst at it, I took the opportunity to fix some of the page data handling. So previously, the code constructed everything using writes of 4K pages and writes of 4 bytes, making up the metadata around it, and system calls are not the most efficient thing on Xen. So this got replaced with the use of write-v, which is a far nicer way of doing things in Unix, particularly in this area. One of the performance tests we have is something like elapsed time to suspend a guest. So part of the scalability tests we do is elapsed time to suspend the largest guest we support, which at the time was a 128 gig guest. Simply, the comparison between V1 and V2 here dropped the total wall clock time from 1 hour and a half to 14 minutes. And that was not, that was basically all in the page data handling, because the legacy in V2 streams, okay, V2 has a tiny bit more metadata in it, but it's looking in the noise compared to the actual page data. This is the scary bit. This is the bits that still don't work. So any guest whatsoever which balloons a page in or out during migration will not look the same on the receiving side. Be aware, this still doesn't work. For HVM guests, the add FISMAP removed from FISMAP isn't represented in the log dirty bitmap, which means the toolstack has no idea that anything's changed. For the PV guests, you do notice that the PV guest changed its P2M, but you mark the P2M frame as dirty, not the frame it was referring to. So whilst you get the correct P2M entry going across onto the far side, you've still got stale data in the frame it refers to. PV guests with structure changes in P2M, this mostly happens only at boot, but also happens later during memory hot add and remove. Nothing ever works out that if a higher level frame changes, the mapped P2M is completely stale, so you end up basing a lot of your calculations on guest RAM rather than a guest structure describing paging. The other issue we came across slightly unexpectedly is HVM guests using populate on demand. At the moment, if there's no signal, there's no way for the tool stack to work out whether something is a pod page or a real page, and attempting to map it causes a pod allocation. So if you started your HVM guest with pod because you literally didn't have enough RAM on your server to start with, you attempt to migrate it and it genuinely runs out of RAM and crashes the VM because the VM was naughty and ran out of RAM to start with. Ideally, the VM should start up and its balloon driver should fix all of these things early on boot, but the balloon drivers are not necessarily the most reliable things around. Oh, sorry. So looking at some of the further work, there's the live migrating looping parameters. At the moment, they're hard-coded. It's something like 5 iterations of the loop and 50 dirty pages for an early pause. The legacy stream did have some parameters that were passed in, and you could easily be forgiven for thinking they had any effect whatsoever on it. So we're currently in not a worse situation with the looping parameters, but there's definitely room for improvement there. The other thing that would be interesting to do is the linear P2M support, which is some work done by Jürgen. Whilst we were developing it, designed in an ability so the tool stack could actually work out when it had changed and take appropriate actions. So yes, those are some of the more general notes. As far as 4.6 goes, we have some fairly good news. It's all fully committed, it's all fully enabled. OSS test is now testing it. From a command line point of view, XL save, restore, migrate, and XL remus all will continue to function as they did before. We completely removed the legacy code. I believe there were some cheers that happened when that commit got accepted. And there should be no noticeable difference to users. It might go a little faster. Any questions? Conrad?
With the improvements you've made, is it also feasible to make it more faster by having it work spread across CPUs? Or is there a lock mechanism that runs the last line to benefit from that?
What improvements are you thinking about here?
Migration by splitting across multiple CPUs and using one SSD?
I don't. So the question for the recording is whether you can use more vCPUs to speed up migration. I don't think that's a practical thing to do. It's essentially a linear algorithm, and if you're doing it properly, you're bottlenecked on disk performance or network throughput. It's a lot easier to saturate that than it is to get any further speed from page data.
I'll leave one question. You mentioned there was outstanding issues ongoing. I presume there was still existing with migration in one.
Correct. Yes, all of the outstanding issues are bugs that we didn't expect to find in V1 and didn't fix in V2 because they're hard. We're looking into them, but they are not easy problems to fix. But yes, those are things that were always broken, but at least now we know that they're broken, whereas previously they assumed to work.
How do you deal with interrupts when you're migrating?
Right. The question is how do we deal with interrupts whilst migrating? Do you mean interrupts to the vCPU?
Any kind of hardware interrupts, or devices.
So most of the interrupts will be dealt with via QEMU. One of the things you have to do is pause QEMU. Let's just let that go blank. So you as part of the live migration, you do quiesce QEMU, so it's not generating any more interrupts. The way the PV drivers work is a little bit more special. You need active support from the PV drivers in the guest kernel, and they are required to replay the control ring on the resume side. So that mechanism deals with lost interrupts or maybe a bit of lost memory. What you end up doing is you will either transmit the same packet again twice. I transmit it once on the sending side and didn't receive that in the final image sent over, and then you send the same packet again on the receiving side. That's fine. Network will cope with that. For disk, you may get two identical writes to the same sector, which is essentially a no-op. It's a little bit inefficient, but.
Yeah. What about if you have hardware pass-through from the source?
There is no current support for doing hardware pass-through and migration. You cannot perform log dirty on a VM that's got hardware pass-through because you can't get replayable faults from the IOMMU. What we've seen some people do is have something like a virtual function network driver in the guest. So they will bond a PV network interface with an SRIOV device, and when you want to migrate it, unplug the SRIOV device, let the bond failover keep the network active, migrate using only the PV device, and then replug a new VIF on the receiving side. So that's a compromise that allows you to get hardware support the vast majority of the time and also migrate in the middle. But whilst the migration loop's going on, you can't have hardware in the guest.
Thank you.
So how hard would it be to extend the system to have some sort of live calling mechanism where you can effectively migrate one machine to the same physical host to have a live copy of the same machine?
So there was some, the questions to do with live cloning. There was some work done by Gridcentric a while ago where you can basically set the entire VM copy on write. So you don't need migration for that. There's already a way, or supposedly a way, to just pause the VM, mark it entirely copy on write, and then use mem access to deduplicate pages as they come in on the faults.
Right, what requires the original VM to be paused, so I'm talking about live cloning where both machines will keep running.
So you pause it, mark everything as copy on write, then unpause it, at which point you... I think quite a lot of that was actually hidden away in their proprietary bit. There is an example that apparently does this. I haven't looked into it too much, but certainly the technology is supposed to be there, present and available to work.
Hey, I was wondering if you can describe the requirements on hardware when doing migration, if there are any, and also requirements perhaps on matching hypervisor solutions on the, when one is doing the migration, and/or possible issues that likely have come up or are considered when differing hypervisors versions might be used.
So typically speaking, for actual live migration itself, there's no hardware support whatsoever. Logdirty is implemented in software in the hypervisor. One of the features for Zen 4.6 is Intel page tracking, which is a hardware optimization that allows Logdirty to be more efficient, but that's just a performance boost if you need it. There is no specific required hardware support for migration. It's all software. For differing versions of Zen, typically you can only move forwards, or rather on the same or newer. So there's forward compatibility maintained like that. In a lot of cases, you can go backwards, but don't. There's a bit of a rat's nest there. It may work in some circumstances, but it's definitely not supported.
So just to clarify, it seems that you indicated that there's no requirements per se on hardware when doing the migration. Have there been no issues when doing migration from one type of system to another type of system?
There's a whole lot of fun if the two vCPUs are not the two CPUs are not identical. Part of that I'm working on at the moment to fix with the feature leveling improvements. There's more that needs to be done, but there are definitely bugs there. We're working on them.
Okay, thanks.
So I have two questions. So does the stream have any concept of encryption, or is that treated external to the stream?
Okay, the question was to do with encryption on the stream. No, we just read and write in and out of a file descriptor. XL uses SSH to do it. Zappy, I have no idea, it probably encapsulates it in a JSON blob. That's essentially how you choose to set it up. All the code here does is use a file descriptor. So that's up to the hosting environment as to.
And then my other question was on the looping, is there any kind of, are you coming up with some kind of algorithm to determine convergence so that you don't have it fixed?
So the other question is to do with the looping and converging on an optimal. That was what I was referring to into the more work required area. Yes, it would be nice. It's not currently there at the moment. Yes?
You have mentioned HVM params.
HVM params, yes.
What about them? When do you migrate them? The beginning of the migration, in the middle, and what do they change?
So HVM params are migrated at the end after the VM has been paused. HVM params are quite nasty. They're the wrong solution for just about everything they're currently used for. I would love to get rid of them completely, but they're a little bit too much baked into the API now. There is a small list of them that get sent, which is the list that I thought were relevant to be sent to the far side. That may need to be tweaked as we go along and gain new parameters. But yes, that is done adjacent to the HVM context blob that is after the VM has been paused. So it's in the critical region, the critical downtime region.
Is there a plan to like implement a hypercall to read and write them all?
That would be optimizing the case that isn't the slow part. You could do if you want to, but there are many better places to go and optimize first. Apparently, I'm a lot out of time. Oh, sorry.
So when's our next speaker? C1 from Intel? There we go. Thank you.
Thank you.